Okay, can everybody see the screen? Okay. So today's session use we will learn about BERT. Well, you actually learn what is BERT at Tuesday section. And today we will learn how to use BERT to do some task on natural language processing. I will mute all, sorry. Okay. So just for a reminder, what is BERT? BERT stands for bidirectional encoder representation from transformer. So as you learned last week, the transformer is composed of two parts, encoder and decoder, and BERT only uses encoder. So why is it bidirectional? So bidirectional means that you have to understand certain word by looking at the previous word and the next word. So as you learned, BERT is trained with two tasks. One is masked language modeling. So you mask certain part of the sentence and the task is to predict what should be the mask. So this is the input and this should be the output, and the target is here what and here is said. And another task for training BERT is next sentence prediction. So given a pair of two sentences, you predict whether the two sentences entail or not. So here label is next because it is somewhat related. So it is next sentence, and if it is not, the label is not next. So this is two-class classification. Oh, sorry. Two-class classification, and by training BERT with these two tasks, you can get a BERT. And BERT uses training corpus, Toronto Book Corpus, and English Wikipedia. This has a lot of words and sentences. And as you can see, the original transformer has an encoder and decoder, but BERT only uses encoder, and GPT-3, it only uses decoder. We will not handle GPT this time, but this is the difference between BERT and GPT. And BERT is simply a pre-trained stack of transformer encoders. And how many encoders are there? There are 12 for BERT base and 24 for BERT large. And is this thing? So is BERT useful for practice? So actually, BERT is widely used since now. It was introduced in, I think it was like 2019 or 2018, but it is still used now. It is simple, and there are a lot of tasks that you can do using BERT. Today we will do sentiment analysis, but if you go other websites and see what BERT can do, there are tons of things that you can do. So you will learn this time sentiment analysis, but later you can do much more tasks. One thing to notice is that, as you know, BERT is only the encoder architecture. So if you want to generate something like summary, if you want to summarize something, or if you want to question, if you want to, like, what should I say? If you want to generate certain utterance, you can use BERT. Then you have to use GPT-3, which has a decoder, or like another sequence-to-sequence model like BART or T5, you may heard of it. So in general, we use BERT when we have to do some classification task. But if you want to generate some words, and BERT is not the good choice, but BERT is still good. So today we will see how BERT works. So first, in this section, we will learn how to fine-tune the pre-trained BERT for sentiment analysis. And we have to do certain like text processing and classifier using Hugging Face library. And today you will learn what BERT is and how to pre-process text data for BERT, and how to use transfer learning to fine-tune the pre-trained BERT to your own task. In this case, it is sentiment analysis. And how to evaluate the model on test data and predict sentiment on raw text. So I think maybe today's session is the most important for you guys who want to do the NLP task, because it is still used today. I use it, and today will be very useful for those who want to do some NLP tests. So as usual, first of all, we change the run type to GPU. Yeah. And first of all, we have to install the Hugging Face's transformer library. So you install this. Okay. So if there's any question, or like if there's an error when you are running the code, please don't hesitate to ask. Okay, so we pip installed transformers library. This is Hugging Face library, and we import transformers and other libraries that we need for today. So we import all the libraries and set the device to CUDA. Okay, so the CUDA works fine. And for the data set that we'll use today, we will use the Google Play app reviews dataset. And when you just run this code, it will download immediately. Yeah. So this is the dataset for today, and this is how the data frame looks like. So in this data frame, you only have to look contents and score. So content is that, excuse me. Okay, content is what is the thing that we have to classify. So in this case, I cannot open the app anymore. So he or she is not happy about this app. So he or she gave a heuristic score. I think score 1 is bad score. Yeah, score 1 rating. Yeah, so score 1 is the lowest score. So he or she is not happy about this score. So he or she gave a score 1, and another one is very costly for some premium version. Like he is unhappy about the cost, so he also gave the score 1. So this is what we have to classify today, and this is the input. So let's pre-process this data. So if you look at the data frame shape, it has about 12,000 rows and 12 columns, but among these 12 columns, we only have to use content and score. And let's look at the information about this data frame. So we will use content and score, and the score is int type, but content is object, which is string type. So if we don't have, so we only will use these two. And let's see how the score is distributed. So we will use Seaborn's count plot, and let's see. Yeah. So this is the review score. So this score is this score here. And if we count plot this, the lowest score has about 2.5 thousand, and the 5 score, which is the maximum, has the largest. And we'll have to predict these scores according to the content. And actually, there are 5 labels, top 5 categories to classify, but it is easier if we just narrow it down to just 3. So we will change the data frame to only 3 labels, which is negative, neutral, and positive. So when the score is below or equal to 2, this part we will classify as negative. And when the rating is 3, we will classify as neutral. And when it is 4 or 5, we will rate this as positive. So we make the mapping function and we apply it to the data frame and another new column sentiment. So yep. And let's again see the count plot for the changed output. Yeah, so this is changed to this one, and there are only 3 categories: negative, neutral, and positive. And we will use this as our training data set. Okay, so yeah, so you guys will all know that the machine doesn't understand the text. They only understand numbers. So we have to change the text into numbers. Well, it can, and you don't have to, yeah. So use this in this session, we will see how the text is transformed to IDs, which is numbers. So today's section, we will use BERT base case. So there is another one called BERT base uncased. So what is the difference between cased and uncased? So the difference is that in the cased, A and A is differently recognized by the model. But for the uncased, A and A is same for the model. So this is the difference between cased and uncased. And why am I using cased this time? This is because, so here you can use a cased or an uncased version of BERT and tokenizer. In this case, the cased version works better because if you look at the review, this like 3 capitalized bad might have more negative meaning than just low letter bad. So in this time, case can be the better option. And as you saw here, wait a minute, yeah. So BERT base has 12 encoder layers and BERT large has 24 encoder layers. So if you want to use BERT large, and you can just change here BERT large cased, or if you want to do uncased like this one. So this time we will just use BERT based case. Yeah. And first of all, we have to bring the tokenizer. So there's a BERT tokenizer we imported from here. BERT tokenizer we imported from Hugging Face library. So we put this BERT based case argument in here. And this brings the pre-trained tokenizer from the Hugging Face library. So let's run this. So it will download this BERT based case tokenizer from the Hugging Face library. And we will see how to tokenize certain text with this tokenizer. So this is our sample text. Nice to meet you. How are you? And let's see how this works. So if we want to tokenize this, there are 2 steps to tokenize. So first, we change the text to chunks. So this means like nice to this. So this is actually tokenizing process. So we tokenize all this one sentence to subwords, and next, since the model or computer can understand what is nice, what is true, so we have to change every subwords to ID. So tokenize function is doing this task, and convert tokens to ID function is doing this task. So the tokens, so if you run this code, here tokens is this one. So as you can see, it is well tokenized. And if we convert tokens to IDs function, it'll automatically change these words to the pre-built dictionary. Using pre-built dictionary, they will change every single word into integer ID. So when you are inputting the words to the model, you have to input these, not this or this. Yeah. So is there any questions so far? Is everybody following up? If you have question about this, anything, you can ask anything. So yeah. So this is the two step to change the sample text to IDs. But as you can see, there is two process, and it is, you don't have to do it in two process. We can do it one process by just giving sample text into the tokenizer. So this is the difference. In this case, we tokenize and convert tokens to IDs, but you can just do it once. So as you can see, this input IDs is this one, and I will explain what is this and this. So first of all, you can see this and this one is different. Mainly, there is 101 at the front and 102 at the back, but they don't have this one. So what is 101 and what is 102? This is actually the special token that explains to the model that it is the beginning of the sentence, and this one is the end of the sentence. In BERT, you always have to use this special token. So when you use this function, it automatically puts the special tokens that you need. And so yeah, so this is a difference. And attention mark, everyone knows what is attention mask. So attention mask tells the model that at what token that attention should be made, or where the attention should not be made. And token type IDs is actually, we're just using one. So let's see how it works. So let's make another sample text. Sample text one is hi, and sample text two is my name is Jane. And let's tokenize sample text one, sample text two, and yeah, let's see how this works. So you tokenize this two sentences together, and this has only one list, but in this token type ID, it is separated. So this tells you that the front three is different with the another 6 tokens. So this is because this hi is made with this one, and my name is SJ is this one. So token type IDs tell you that this one and this one, these two sentences are different sentences. So if you want to use two sentences at the same time, you have to use token type IDs. But if you just want to use one sentence and tokenize it, and it is always 0, so you don't have to use this. And let's see more about the special tokens. So there are a lot of special tokens like separation tokens, ELS token, beginning of sentence token, end of sentence tokens, unknown token here, unknown token, padding token. But so let's see how it works. So if you want to know what is, so all these, for any model you use, there's always separation token, CLS token, pad token, and UNC token. So if you want to check for another models, like if you want to do it on BERT or T5, you just load T5 here, and the process is same if you want to see what is the separation token for T5. So let's run, if you run this for BERT, and it tells you what the BERT separation token is and its ID. Also same for the CLS token. So, actually in BERT, the CLS token is used as the beginning of sentence. So in this case, all the tokenized IDs had CLS token at the front. And if you want to pad something, there is a pad token and it is 0. And if the model sees unknown text, the word that they don't have on their dictionary, they change it to the unknown token. In this case, it's UNC, UNK, and the UNC token will be this one, and the ID will be 100. Yeah. So using all of these, let's tokenize. So there's two options. So at first we tokenize the word and convert it to token IDs, and I told you that this can do it you can use either this part, this one, or this encode plus function to do all at once. This time we will use encode plus. This is same, actually this is same for just not using and just using, what is it? Just using this one, but as this script is made with this one, so we'll use it. So here comes the sample text and what is truncation. I'll explain what is truncation, what is max length. So add special tokens. True means you have, please add CLS or separation or like pad token. And return token type IDs false. What is this? So here, this is the token type IDs. And as I told you, if you are just tokenizing just one sentences, token type IDs is no longer used. So we don't have to return it. So we return it to false. And I will explain this. What is this? And return attention mask. This is attention mask. And we need attention mask to input to the model. So we need attention mask and return tensors. So what will be the return tensor types? So PT means PyTorch, and we have to return the tensors to the PyTorch types. And yeah, I'm sorry. So let's encode this and see how this works. So the output is encoding, and encoding has two types, input IDs and attention mask. We erased return token type IDs, so there's only two. And I'll explain what is truncation, max length, and pad to max length true. So I'm sorry, but I will have 5 minute break. Someone come to my house, so I'm sorry, but I will have 5 minute breaks. I'm sorry. Oh, can everybody hear me? 아, 죄송합니다. 제가 그 등기 우편이 왔어가지고 갑자기 I'm sorry, because of the postal service, I had to take something, so we'll review we'll see again this one. So okay, so what is truncation, what is max length, and what is pad to max length true? So yeah, let's see here. So in this particular case, we are just tokenizing just one sentences. But if you as you all know, we train the model with batch. We don't train the model with just one training data. We use batch, and let's say that if the batch has the sentences like "I like you," this is very easy, very short. But if there's another sentence like any long sentences, and yeah, let's see if there's two sentences. So if you want to tokenize this one will be maybe have 5 tokens. CLS token, I like you, CLS, so there will be 5 tokens. But if you tokenize this one, there will be like more than 10 tokens. But as you're using it as a batch, these two has to be same. The length of the tokenized output should be same. So in this case, we pad it. There's two choices. We pad it or we truncate it. So what does padding means? So padding means that if you tokenize this and say that the tokenized output is 101, like 1, 1 to 3, 1 to 4, 1 to 5, and 101, 5, 5, and this is the lower one is like 101, any number, say any number, 101. So if we pad it, this means that we pad it with this one. We pad it with padding token. With this time, the pad was 0, so we padded with to make it the length same with the below one. And what it means to truncate it means to truncate the longer one. So this is longer, so we truncate it like this. No, this, so that the length becomes same. So there is an argument called max length. So when we set truncation to true and max length to 32, and if the length is above 32, it erases to make the sequence length 32. And pad to max length true. This means that if the length is 20, you pad tokens 12 padding tokens to make length 32. So this is how the truncation and padding works. Can everybody understand? We'll see examples in how this works again. So let's see. Well, first of all, this is only one example, so you don't need to use padding or truncation. But okay, let's see how the encoding. So if we, as you see here, where was it? Yeah. If we just encode it with no padding, this is the output. This was the output. But when we set the max length 32 and pad to max length true, this is same. This is here is this one, but they automatically concatenates the 0 padding tokens to make the length 32. Can you see the difference? So this is how it works. And also same for the attention mask. So if you see the attention mask, the length is same with the input IDs, but at padding area, the attention mask is 0. So this means that you don't you don't have to make an attention at this padding mask. You only have to make attention only here, this part, and you don't need attention here. This transformers library automatically tells you that there is no need to attention on padding area. So yeah, very convenient. And if you want to make the token IDs back to the text, like you want to make this one add back to text, you use convert IDs to token function. And if you use this, yeah, it'll show you the original sentences, including special tokens. And so we learned how to tokenize it, and so in this time I just set the length to 32, but this is the hyperparameter, and you always have to set this max length based on your data set. And so this time we'll experimentally analyze what max length we will use. And so for the data frame content, so this data frame content was, what was it? This one, these contents. So we see how the length, all the lengths looks like, and so for all texts, we tokenize it with 512 and see how the length looks like. So we set 512 as a maximum, but it will definitely max length. Yeah, so okay, the question was, does the max length influence the performance of the model? My answer is absolutely, because if you set the max length to like 3 in this case, how are you will all be erased. So if I set this like this one, if I set this like 4 and C, it erases all, and there's only nice and 2. So then the model cannot learn properly. But then somebody can wonder, if I just set this max length to like 124, then there will be no problem. But if you set this like this, there is like 124 unused padding tokens here, and this is not good for the model. We only use this part, these like 7 or 8 tokens, but if you set this 1024, there are too many unnecessary tokens. So this is the hyperparameter, and in this session we will see how to set this hyperparameter. So we appended all the lengths of the tokens at the training data that we will use, and let's plot this. And this is the token length for our data set. So by looking at this graph, we set certain point for the max length, and so in this case, the most of the sentences are below here. This is maybe 125. So most of the reviews seem to contain less than 128 tokens. So, but we will be on the safe side and choose the maximum length of 160. Yeah, so below 160, everything is inside. So we set the max length to 160. This is how this way we choose the max length. And okay, so for now we learned how to tokenize using BERT's tokenizer, and we also learned how to set the max length when we have certain data set. So based on this, we will make the PyTorch dataset with our data set. So yeah. Oh, besides, is there any questions so far? Okay, so let's move on. Yeah, so let's make the data set. So the data set takes reviews, targets, tokenizer, and max lengths. And as you know, that when you're making the PyTorch data set, you have to make always have to make two functions, length function and get item function. So length is just outputting the length, and get item is, so in this data set, we not only just output the text, but we also output the tokenized output. So in this tokenizer, we output review as special token. And same as before, but this time the max length is the max length argument we set here, this one, as we will set this one. And return token type ID is false, we don't need this one. Pad to max length true, return attention mask true, yeah. And so the returned output will be review. This is just the simple text, and this is the tokenized output, and this is the attention mask, and this is the target, what the label, and why we flatten it. So why we flatten it. So where is it? So yeah, if we don't flatten it, oh yeah. If you don't flatten it, there is a list inside the list. So if we flatten it, it just becomes one list. So this is why we flatten it at the end. So we flatten input IDs and attention mask. And let's see. Yeah, so we build this class and take reviews as df contents. Where is it? df contents, this one. And the target is sentiment. We made sentiment by map by this one. We made sentiment. And tokenizer. This tokenizer is, where is it? This tokenizer, we use BERT base case BERT tokenizer. We also put this as a class function. And max length is 160. Oh, actually, you can, as we use, we'll use this. Yeah. So let's do this and see how the data set, how many data sets are there? There are 100, 2, 4, 5, 9. And if we get the review text item, oh, so, yeah, oh, I don't know why this works, but okay. So for the first data set, this is, I cannot open the app anymore. He's not happy about this app. And let's see the targets for it. So what will be the target? Definitely it will be 0. So yeah, he's not happy about this application. So, and the tokenized version will be this one. So this is the CLS token 149 will be I, and this is the end of the token. And as we set the max size 160, all of these will be padding token, and same for the attention mask. If the size will be under 60 and the attention mask it's a 0 for padding tokens. And so we are finished with our data set, and let's split the data set. So we split the data set, see how the data set looks like. So training has about 10,000 and 625 for each valid and test data set. And we using this function, we create the data loader and set the batch size 16 and create train data loader, val data loader, test data loader. So for train data loader, let's look at just one sample. Yeah, this is how it looks like. So here 16 means the batch size. We set the batch size. Where is it? Batch size is 16. So this is the batch size, and this means the sequence length. So you have to remember that input IDs and attention must always have the same size, and targets is 16. And let's classify now using BERT. So, where was it? Oh, as you saw here above, we bring the tokenizer using this function. This time we bring the model. This is almost the same as bringing the tokenizer. So let's bring the model. It'll download it. Oh, it's a design choice. You can use whatever option that you want to use, but there is it convenient. In this case, yeah, you're right. It will be a little bit small for validation set, but this is just the test. So, but if you are actually deploying a model, then in my case, I prefer to split like 8 by 1 by 1. But as you said, this one is 9 by, what is it, 18 by 1 by 1 in this case. So this is design choice, but you can change this size and practice by yourself. And so we downloaded the BERT model, and the BERT model takes conventionally two inputs. The one input is input IDs from here, and another one is attention mask. Attention mask is from here, and return dict false is whether you are outputting in the dictionary format or tuple format. So when we set this false and the tuple is coming out, so we all know what is the input and what is the output. What is the output? So what is the last hidden state and pulled output? Oh, is there? Oh, where's one of these? Let's see how it works. Yeah. So last hidden state means this one. This is the last hidden state. So this means the output of the CLS token, the first one, and pooled output. Oh, actually, I think I'm wrong. Oh, wait a minute. Why is it wrong? This is actually, let's set it to 16. This encoding has 16, so yeah. This may work now. Yeah. And so there are two output, last hidden state size and pooled output size. So what is the difference? So last hidden state size means all the vectors here. So if we say there are 16 sequence lengths, this is these all outputs will be the last hidden state size. So it has batch each dimension means batch size, sequence length, and hidden size. And pooled output size is actually the BERT model itself gives the summarized version, summarizing by deleting the sequence length. So summarizing all the 16 tokens, and in this case, they linearize and tangent hyperbolic functions use, and so this is for summary. That last hidden state means this output shape will be batch size, sequence length, and hidden size. So output of all sequences, and the pooled output size is the output shape is batch size and hidden size only. There is no sequence length, and this is the summarized is it right? Summary? Oh yeah. Summarized version of sequences. So this is 16. And why is 768? This is the number of hidden units in feed-forward networks. Yeah, you can verify it using this hidden size. This is BERT model uses 768 dimension as a hidden size. So this output will be the 768. And here's the pooled output is the summary of the content. So you'll use pooled output as the sentiment analysis. So maybe later, if you want to use only like this token's output or this token's output, then you will use this one. But if you are using the sentence as a whole, then using pooled output will be the good design choice. So let's make the classifier using this pooled output. So we have one input. This is n classes. In this case, will be 3, negative, neutral, positive. And so we define BERT model, dropout function, linear function. A linear function, the input size will be the hidden size. In this case, it will be 768 to n classes. N classes was here, and it will be 3. And the forward network. So as I told you, we will not use last hidden state this time, only pulled output. So we set the last hidden state size to just underscore, and we will only use this one. So the BERT takes input IDs, attention mask, and return the faults, and we drop out the output of the BERT, and we linearize it to this dimension. So one more time for all the dimensions, how is it pulled? Average pulled? Well, it differs on what model you use, but in this BERT model, in this particular BERT model, the pulled output is last hidden state size first token, it is linearized, and it is hypertangent aged. It is non-linearized. This is how the pulled output for this BERT model, but if there are a lot of transformers models, so let's see. So there are a lot of models: BERT base case, distilled BERT, raw BERT. You may heard of it. Facebook's BERT base, XLM, GPT. There are a lot of T5 base. There are a lot of transformers library, and all of these libraries have different pulled output functions. So in this case, we use the pre-built pulled output function, which is this one, but it is not always fixed. It depends on the model. Okay, so let's see. So the input ID here, input ID's shape will be batch size, sequence length, and yeah, that's it. And attention mask will be same. Batch size and sequence length. And if we put in by this side and the pulled output size will be, what is it, batch size by hidden state size. Hidden size. This was 768 this time. And we drop out, this will still be same. Dropped out output will be still, it doesn't change the dimension, so it will still be batch size by 768. And here we use the linear function to be 768 to be 3, and so the final will be batch size by 3. Next. So the question, 전소영님 혹시 이 히든 스테이시 이걸 말씀하시는 건가요? Okay, the question is, if the max length is fixed, how the last hidden state size is turned out? And okay, this 16 actually comes from not here, not this one. Where is it? What's the encoding? Ah, yeah, here, this one. Yeah, here. This encoding is that encoding is used from here. The max length was 16. I'll bring this back here. Oh, you got it? Yeah, so if we set this to like 555 and then like 33 and run this, and you'll see what will be here. It will be 333. Yeah. But still, the pulled output will be 1 by 760. Yeah. Okay, so I hope you all know how this model works, and the output size will be batch size by 3. So we use this, and so we take len class name to 3 and take this model to device. Oh, what's wrong? Oh yeah, sorry. Okay, and let's see how this works. So what is sample batched? Where is sample batch? Ah, sample batched is the batch the first training data loaders data. So let's see how it works. So we take input IDs as sample batched input IDs and put it to the device and attention mask. So as I told you here, the input ID shape will be batch size by sequence length and attention mask will be the same. And we'll see how it works. So it's same. It's 16 by 160. Why is it 160 this time? The sequence length. This is because for our data, for our real data, we set this max length to 160. So this is why the sequence length is 160. And if we just model input IDs and attention mask, can someone tell me what will be the shape of this if I run this code? Oh, it's size actually. Can anyone guess what it will be the output size? So no one? So the model output size of the model, as I told you, output size of the model is batch size by 3. So if the batch size was 16, so if I run this, it'll be 16 by 3. Yeah, 16 by 3. So this will be 16 by 3, and we softmax with dimension 1, and the output will be, of course, 16. Oh, no, it's 16 by 3. Yeah, 16 by 3. The size will be 16 by 3. Yeah, so now it's done. Let's train this one. So we set epochs 10 and optimizer Adam W and total steps. Scheduler, we will use get linear scheduler with warmup. I don't have time to explain what is this, but simply when they increase get linear schedule with warm-up means you increase the learning rate, and when the model doesn't improve anymore, it decreases. This is how the get linear schedule warm-up works. And we use loss function, cross entropy loss. And here, let's read this one. How do we come up with all hyperparameters? The BERT authors have some recommendations for fine-tuning learning rate to be D3 and number of epochs to be 2 or 3 or 4. And we are going to ignore the number of epochs recommendation, but stick with the rest. So we will use epochs 10, and actually this sometime, so I will just use 3 actually. And okay, let's define training function. Set model to train, losses for data roller, we put input IDs to device, attention mask to device, targets to device, and seed output, and the output shape. Once again, the output shape output size will be batch size by 3, and we max it with dimension according to dimension 1. So the max function outputs max value and max indices. We don't need values, we just need indices. So we set this to underscore. And what will be the output then? The output softmax를 통해서 나온 16/3 텐서는 어떤 의미예요? So if I don't do the softmax, it is just like any number. But so the question is, what is the meaning of the softmaxing the output? So the answer is, if I don't use softmax, it just outputs any score from the BERT, but we cannot use this one. So we have to make it as a probability. So in this case, we make all these elements by making it to the probability. So we make this one as here, and as you see, the sum of this row is all 1. So the meaning, what is the meaning? The meaning is that for this certain sentence, this is the maximum probability, and this was the positive sentiment. So they classify as positive for what will be for this case, for this sentence, the positive, the largest probability is 0 label, so it will be classified as negative. This is the meaning of softmax. Yeah, so where was I? Yeah, so we max it and calculate the loss, and we append the prediction, we append the item. We also see how many correct are there, and we backward it, and we use grad norm, clip grad norm. So if you want to know more about this clip grad norm, please see this slide. And we scheduler step in 0, and eval will be same, except we use this one and this one. The rest is almost the same. There's no back propagation. And let's run this. I don't know how long it will take. Maybe it will take some time. Oh. Yeah, it works. How long it'll take? About 5 minutes for one epoch. How long is that? Maybe let's just see one epoch, and I will left it for you guys to train by yourself. So while training, is there any question? Is there any question? So what will be the last? I'll briefly explain what will be the last. So they just we just actually I wanted to download this file because it takes some time to train all, but this Dropbox link doesn't work anymore. Oh, there was a question. 포지티브랑 네거티브를 구분하는 게 저희 태스크입니다. 태스크에서 그렇습니다. 저희가 지금 여기 구글 앱 평가 데이터셋으로 지금 여기 위에서 구글 앱 평가 데이터를 다운받아가지고 얘네를 이제 태스크로 쓰고 싶기 때문에 얘네들이 지금 1, 2, 3, 4, 5점 3개, 5개가 있었는데 이 레이블이 5개가 있으면 너무 많으니까 간단하게 그냥 저희의 토익 샘플 하기 위해서 얘네를 1, 2점은 네거티브, 3점은 뉴트럴, 4, 5점은 포지티브로 해가지고 3개로 바꾼 다음에 이제 그 끝에 3의 의미가 이제 16 by 3에서 3의 의미가 이제 이 3개입니다. 레이블의 개수. 오케이. 50% is done. So this is just plotting the accuracy and the rest of it is actually very simple. If you just run this for 10 epochs, the rest will be easy since there's not much time. So, okay, I think I have to stop today's lecture here because, so if you want to reproduce all these the codes below, I recommend you to set the epochs to 10. Maybe it'll take time, but it'll show great results below what we would below. So I recommend you to set this epoch to 10 and train by yourself. If you want to see the progress bar, you import from TQDM, import TQDM, and put TQDM in front of data loader. This is it, and this will show you the progress bar. And so one epoch takes about 5 minutes so training 10 epochs will take about 50 minutes. So after training all this data, you run this code below. You don't have to run this. Don't run this. And see how it works. And if there's any question regarding the code below or anything regarding BERT, feel free to ask on custom, then I'll answer. Yeah, so this is it for today, and yeah, see you next time.